In this video, we'll be looking at solving for equilibrium concentrations for a system that is not yet at equilibrium. Oftentimes in a reaction, you'll be given some amount of reactants and products, but there's no reason to assume that reaction is at equilibrium. However, we oftentimes do want to know what the concentrations will be once it reaches equilibrium. We're going to be utilizing a tool called ice charts to help us solve for this. As an example, consider the reaction here. You have carbon monoxide reacting with water to form carbon dioxide and hydrogen gas. The volume of the equilibrium constant, KEQ, is 1.845 at a given temperature. We place 0.5 moles of carbon monoxide and 0.5 moles of water in a 1 liter container at this temperature and allow the reaction to reach equilibrium. What will the equilibrium concentrations be of all substances present? The first thing I'd like to do here is figure out what our concentrations are. And it's given us that we're in a 1 liter container, which makes it really convenient because that's going to mean that the amount of moles we have is also the molarity. For example, with carbon monoxide, 0.500 moles divided by 1 liter gives us 0.500 molar. And the same thing with H2O. We have a 0.500 molar H2O concentration. Now what I'd like to do is set up the ice chart. To do that, I'm going to rewrite the equation. We have carbon monoxide reacting with water vapor in equilibrium with hydrogen gas and carbon dioxide. The ice chart gets its name because of the 3 different lines we're going to set up: an initial concentration, a change in concentration, and an equilibrium concentration. We were given the initial molarities of 0.5 molar carbon monoxide and 0.5 molar water vapor. We were not given any product, so those things can both be set to 0 molar. When this reaction begins, there is only reactant to begin with. So we know that the initial shift is going to be from the reactant side to the product side, that we will lose X molar of both reactants and gain X molar of both products. Now what I'd like to point out here is the coefficients. All the stoichiometric coefficients in this case are implied to be 1s. That's why we're losing 1x from the reactant side and gaining 1x from the product side. If, for the sake of argument, one of the coefficients was a 2, we would instead gain 2x molar of hydrogen gas. Again, those stoichiometric coefficients tell you the ratios in which reactants are lost or products are gained. However, in our case, all of those coefficients are 1s. So we're now able to set up equilibrium concentrations. We don't know what X is, but we can use an expression. The equilibrium concentration for carbon monoxide will be 0.5 minus X. For water vapor will be 0.5 minus X. For hydrogen gas will be X. And for carbon dioxide will also be X. What we can do at this point is use those equilibrium expressions and the KEQ expression to solve for X. KEQ, as you remember, is equal to products divided by reactants. In this case, KEQ equals the concentration of hydrogen times the concentration of carbon dioxide over the concentration of carbon monoxide and the concentration of water vapor. KEQ given in the problem was 1.845, which in this case is going to be equal, we're going to zoom out a little bit, is going to be equal to the concentration of hydrogen times the concentration of carbon dioxide divided by the concentration of carbon monoxide and the concentration of water vapor. So what we have here is an ability now to solve for what that value of X is. And doing a little bit of algebra, you find X is equal to 0.288. At this point, I want to return to my ice chart right here. I'm going to slide some of my algebra down a little bit to give myself more space, because now that I have a value for X of 0.288, I can solve for the equilibriums. Equilibrium is 0.5 minus 0.288, 0.5 minus 0.288, 0.288, and 0.288. Or, written another way, scroll down one more time, the equilibrium concentrations are going to be 0.212 molar, 0.212 molar, and again 0.288 molar and 0.288 molar. Let's consider another problem now, but I'd like to add in the additional rule. When 100 times the KEQ is still less than the initial concentrations you're given, you can leave out the minus x or the minus 2x in the math. And what this means is that when KEQ is that small, the value of x is going to be negligible and won't change the initial concentration in the subtraction. Doing this is going to simplify the math without changing the final answer based on significant figures. So just as an example of this, let's say you were given some sort of reaction A plus B in equilibrium with C and D. If your concentration of A was, for instance, 0.5 molar, and your KEQ was, we'll say, 1 times 10 to the minus 8, well, that KEQ times 100 is still significantly less than 0.5 molar. So for our change in equilibrium of 0.5 minus x, well, we can simplify that just to 0.5. And therefore, at equilibrium, the equilibrium would remain the same. The idea here is yes, to simplify the math, but it's also that because of the magnitude of KEQ, there's going to be an insignificant shift in matter from reactants over to products. So with that rule in mind, let's look at this problem here, where HI is in equilibrium with H2 and with I2. For the equilibrium reaction above, 3.6 moles of HI is placed in a 2-liter evacuated flask. The equilibrium constant is given as 6.56 times 10 to the minus 8 at this temperature. Our first step, as always, is to write a KEQ expression of products divided by reactants. And our next step will be to set up an ice chart. Again, we have an initial, a change, and an equilibrium. Here our reaction to HI in equilibrium with H2 and I2. We have 3.6 moles in a 2-liter flask. So thinking about molarities as moles divided by liters, this will give us a 1.8 molar solution of HI. Excuse me, 1.8 molar, not 18 molar. And no H2 and no I2. Our change, there's only one direction that this reaction can shift in, and that's to the right, because there's no product to begin with. So we'll be losing 2x HI, again due to the coefficient, and gaining x moles of H2 and x molar I2. So our initial equilibrium values would be 1.8 minus 2x, x, and x. But remember our rule, 100 times the KEQ is still going to be much, much less than our initial concentration. So I'm going to ignore that minus 2x. I'm going to revise my equilibrium concentrations as 1.x, x, and x. Now don't worry, we're not creating matter out of nothing. It does seem as if we started with 1.8 moles and are going to end with 1.8 moles plus a little bit more. But because of significant figures and rounding, it really will appear that way anyway. Now what I need to do is take my equilibrium concentrations and plug them into the equilibrium expression. KEQ, again, equals H2 times I2 over HI squared. And in this case, our KEQ is 6.56 times 10 to the minus 8 equals x times x over, in this case, 1.8. And as you might notice, that's going to significantly simplify our math. X will be equal to 4.61 times 10 to And I apologize that I missed the squaring in the denominator earlier. That should clear that up. So to finalize my ice chart, I'm just going to plug in my values of x there. My equilibrium concentration of HI will remain 1.8 molar, and my concentration of both products will be 4.61 times 10 to the minus 4 molar. So again, you've seen two examples now of using ice charts. The important rules to remember is that the stoichiometric coefficients will change the amount of reactant and product gained and lost. And in cases where KEQ is very, very small and starting concentrations are large, you can ignore that minus x or minus 2x in this case to simplify the algebra. As always, thanks for watching.